The speaker today is Stanislav Kirdey. He's working at Netflix, where he focuses on large-scale applied machine learning in the areas of NLP search and anomaly detection. Outside machine learning work, Stanislav is obsessed with RuPaul's Drag Race, Pose, and Star Trek, of course. This talk will mostly be an overview of self-service reinforcement learning tools that help to optimize schedules of automation tasks and help to reduce time to detect failures in software, hardware, and cloud infrastructure. In this case, an agent learns the best order of execution of automation tasks to either fail fast or find clusters of failures. Lessons learned from this, writing and deploying applied RL service at Netflix will be shared in this talk. So please take away. Thank you very much.
Thank you. Hey, folks. My name is Stanley or Stanislav. Thank you for joining me. I'm currently in San Jose in California. It's very dark evening here. And I'm happy to share with you some of the findings of building an applied online reinforcement learning system for a case where we have to, at Netflix, optimize our resources when we test and verify quality of hardware, such as TVs, set-top boxes, phones, and all kind of equipment where we run Netflix applications that is streaming videos. And the system is called Learner. We will go over in the next 20 minutes or so what is Learner and why it exists, design and architecture, and production use. Let's start with the concept of reinforcement learning. I'm not sure how many are familiar with it, especially running it in production in applied form, but it's a way to use machine learning to maximize reward for an agent in particular situations. So it is often used in self-driving. It can be used in optimization problems, in robotics. And we at Netflix don't use it extensively, but we do use it for optimization. And some of the pros and cons of reinforcement learning, those are mostly about automation and large-scale automation. What I found by building the applied reinforcement learning system is you have several benefits. You can train agents on small amounts of data. It is especially useful when you start with no data in your environment. Like in our example, we might get a new set of hardware equipment that we never tested before. We don't know the patterns. We don't know what heuristics to apply. So it's a perfect environment to bootstrap an agent and let it explore and exploit the environment and learn from its own mistakes. It can help you to detect patterns real time. And I think it's really cool because the environment can change. The TV or another piece of hardware can get a new firmware version, software update, or it can maybe be downgraded to a previous version of software. So that environment affects how it performs, its streaming capabilities, its audio capabilities, and other things. It can reflect changes in the dynamic environments that I just mentioned. And by using deep reinforcement learning, you can also detect nonlinear patterns, meaning you might have a pattern where you have an increase on the y-axis, and you're going to see some increase on, or you're going to have an like xy axis, and you see there is a mutual increase. The data moves in the same direction, or you might have a nonlinear patterns where things affect each other in non-obvious way. If you have reinforcement learning agents that work in online manner, you can easily scale them to thousands or millions of agents. It's very impressive, and I think it's quite a fascinating technology. You can also extend and modify your agents. You can add different reward functions to it, meaning whenever it does some sort of prediction, and you can reward the agent based on the quality of the prediction. If the prediction was good, you can give agent a high reward. If the prediction was bad, you can give agent a smaller reward. And those are the cons from building an applied reinforcement learning system. Is it's complex. You're adding complexity not only of machine learning, but also reinforcement learning. You kind of lose control if you're using deep neural networks to learn your policy. You're losing control of what neural network learns and how it behaves. Sometimes it's not obvious. There is certain learning curve in the reinforcement learning field, and if you might lose the ownership of the project and you have to give it to somebody else, like for example, it happened to Learner project when I moved teams and I went into anomaly detection. It was non-obvious how to inherit this project for another engineer, so we had to do design sessions and some reinforcement learning sessions. And thus the support of this becomes non-trivial. Let's watch a few cat videos that also gives this reinforcement learning in a nutshell overview. So when you set up an agent, in this situation, the agent is a cat. And this cat as an agent is trying to learn how to jump from the one part of the balcony to another balcony. And you can see it has a state of agent initialization. Then it's analyzing the environment. It attempts to jump, and then it gets assigned negative reward, meaning you can do better on the next jump. But while it's learning and while it's doing those 1,000 jumps, you can see that a few days later, the cat becomes proficient in the jumping and it's just perfect at it. And it kind of demonstrates the cat as an agent learn through the rewards, negative and positive rewards, how to actually efficiently perform a task. And here, I think when you talk about machine learning and reinforcement learning, it sounds a little bit scary or maybe complicated or complex. In reality, it is not. Like it might be done in a few hundred lines of Python code. You need to define your agent. You have a function for it where you give it an environment to predict something. You use the prediction, and that use prediction function gives you some sort of a result. Was the prediction good or not good? And then you use that result to reward the agent. And now how Learner is designed and how it works. It has only 2 API calls. So it's a microservice that exposes several API calls, and it does a lot of the legwork for you. It will set up an agent for you if it doesn't exist. It will store the state of the agent in a document store. And it will also allow you to either use the agent prediction or say, hey, agent, I want to execute 5 out of 6,000 available tests. Give me the best combination of them in a best priority, and it will give it to you. And on the backend, it will set up an episode for that particular ask. And then once you execute it, you can reference the episode and say, hey, I used your prediction for this particular episode. And in actuality, when I executed your prediction, it was a little bit off. So you have to reward yourself based on this data to do better. And then agent in the backend in a synchronous manner will learn, will store it updated state action pairs in the experience reply, and will attempt to do a better job at prediction next time. In production, we use Learner to select tests to run against Netflix infrastructure, against particular devices. We have agents that help to prioritize and schedule things to run based on certain area like security tests, networking, performance tests, as they have different patterns. And by splitting those learnings between agents, we can have one agent that is really good at predicting what sort of security tests you need to execute on a particular firmware, on a particular device, and another agent may be as good in networking tests. I think there's probably several thousand combinations of devices and firmwares, and also there's probably 10,000 test cases available to execute. So the combinatorics of it is quite large, and finding optimal schedule is often not even possible by hand. Here is an example of API. It's kind of JSON data where you can see that you have a test one, you have an array of historical results, you have execution timestamp, you have execution duration in seconds. And this is what agent actually predicts. Based on environment, it gives you importance of a test case. And the importance stands for where in the priority of execution this particular test should stand. Do I execute it first, second, or third? You can see that the importance of this particular test is 0.39, 0 being the lowest importance and 1 being the highest importance. And a few days later, after learning in the environment, you can see that agent learned to prioritize test one. I don't remember exactly what happened here. I would assume the test one is something that consistently fails. And test two has a similar prediction that they need to be executed first. But then test three got a different importance, which is what we strive for. In order to kind of measure the success and also train the agents, we measure average execution time of episodes per agent, meaning episode could consist of several test cases or several combination of test cases, or maybe 100 test cases. We measure time to first failure detected. If we want to schedule 100 tests to execute on a TV, we would like to fail early and detect an issue early. So time to first failure, the less is better. We want to measure the position of the first failure. So which test failed? Is it the 5th test in the execution schedule, or the 1st, or the 10th test? Earlier is, of course, better. We want to count a total number of failures in a schedule. Ideally, when we test something, we don't want to see failures, but we want to be aware of how, what is the impact of clustering failures together. The agent often gets into the state of scheduling things that fail together, and sometimes it would even detect that if you execute, for example, audio test, then the system gets in a state when you cannot execute video test. So it will order it in this way, which is kind of cool. And then we also measure the total execution time of an episode per agent, meaning the total amount of seconds it took to execute the whole suite of tests. We have a reward function, several reward functions, which attempts to give us either optimal order of execution without regards to time limits, or it tries to give you optimal order of execution within a time limit of, for example, 30 minutes. And both of them work. The later doesn't get used as often. And after all of this, there is certain profit. This is an example where you see agent predictions on the right and on the left. Those are two different agents, and you can see how many tests are executed, if agent was rewarded for its performance, and eventually you can start with a graph where things executed and fail out of order, but at some point the agent will learn the patterns and try to prioritize executions in a way that you can fail early or cluster them together. And now, okay, let me check for, okay, so no questions, and let me present again. Let me go over the lessons learned. It was non-trivial project to build. I would suggest, if you don't, like if the return on investment is unclear, don't go for reinforcement learning. In Netflix case, there is benefit, as we have so many different devices and so many different combinations of things to run. Having online predictions and online learning actually pays off. I also run experiments before productizing the idea. What we did is we had a conversation with a few data scientists and came with two types of agent. One agent would use deep neural network to do the predictions. Another one would use random predictions. And also there was an agent that would just recommend everything that was previously failed as the most important thing. So if you, in your first episode, you had 10 tests to execute and 3 of them failed, on the next prediction it says just execute those 3 failed tests first. And we had to measure the performance, like what is the mean time to failure, how many fail detected per episode across 3 different agents, and deep neural network agents were superior after a few how to say it, a few days of training and executing things. Unit testing the code, it's super important. I had in the initial state of the system, I had agents training, but they were training for a week and nothing happened, and the measurements were stale, and I was really pissed off. And then I realized that I always rewarded with some weird value, and once I wrote unit tests for everything, I caught a few things, and the agents finally started to learn and perform better with iterations. And it's super important you start with unit tests, especially in this environment. I also pursued simplification. I realized that nobody really cares what is on the back end of the system. It could be quantum computing, it could be pure magic, it could be reinforcement learning. If it's not simple to use, and if it doesn't do its work, people will not use it. So I oversimplified the API with leaving just 2 API calls, and both of them operate on simple lists. You give it list of test names, it returns you a list of test names in different order. And then you give it back list of test names in with the results of the execution. Something failed, something was canceled, aborted. So yeah, I think if I didn't keep it extremely simple, people would not adopt it. Also, it's important to run experiments against some sort of baseline recommendation. I mentioned it in the first point. Random schedules is a good approach, like some sort of straw man experiment. And that's it. I don't have any more slides. I see some questions. Okay, let me just stop Sharing my screen. Okay. Let me go one by one. Okay. How do you, the question from Phil is, how do you decide whether to fail early on the first failure or continue testing and cluster the failures? So thanks for the question. And we actually provide different APIs. So you can set up an agent that will fail early, or you can set up or it's kind of based on the system. Some agents might say, hey, I'm gonna give you everything and you decide how to execute it and when to fail. So we use systems that call agent and call reinforcement learning APIs and then get the data and then decide how, when to fail or when to stop executing. And hopefully it answers the question. And another question from Phil is, what did the architecture of deep neural network look like? It's actually extremely simple. It just, I think, 20 or 30 neurons. And the input is probably 10 dimensions to the neural network. The input contains some information that we can infer through heuristics about a particular test case, in what category it belongs. Is it audio, video, how many times it failed before? And then neural network is actually giving hidden single, it has several single layers with a few neurons in them. So it's not like a simple perceptron, it's multi-layer perceptron. And it outputs a numerical value at the end. And then we use that numerical value. The higher the value, the more importance we give to that particular prediction. And then there is a question from Maria Vasquez. What percentage of failures was present in your data when you were testing out the RL agent during the experimental phase? We did a few experiments. We had some schedules where we knew certain tests would always fail. So we scheduled those to run continuously to make sure that neural networks can predict those and optimize for those. Those are the most obvious ones. And we also had real data in test environment. I don't know the percentage of failures when we did it, because we didn't have any like a training data for it. We just plugged agents in the real environment with the real data in the flow. And they started to give predictions. So we were monitoring those things. And a question from Matthew Toledo. Why did you decide to go with a shallower network over a deep network? It was mainly due to the fact that the input dimensions are not high. We don't have high cardinality data. It's just 10 dimensions. And on average, the executions are probably 20, 30 test cases. So an episode of training is not that complicated for a neural network. So it didn't need to go deeper, as it didn't have to, learn those nonlinear patterns over a data with 100 or thousands of dimensions. Hopefully this one is answered. And another question from Maria Vasquez. If you only execute tests that are likely to fail, how do you give feedback to the agent about tests that were not executed? So when you execute a test that's likely to fail, you can say that they were not executed, and then in the reward function, the agent will understand those and it will ignore them from the reward. We tend to execute things. We tend to execute everything because even though we want to fail early, we also want to kind of explore the whole environment. And in reality, what happens is we have all those tests run, and something fails. We usually don't even see it immediately until somebody checks the agent state once or twice a month and sees, oh, there is a pattern of failures. I really need to go and check on those test cases. The initial idea was, hey, we might be able to alert ourselves if agent picks up certain patterns, and we need to maybe remove tests from rotation, not let anybody run those. But in reality, we don't have enough people to actually monitor those agents, so they do whatever they want to do, and they tend to execute everything and then cluster things on their own, and somebody will look at it once in a while and say, hey, yeah, those are definitely broken. They've been continuously failing. They've been failing in a cluster, and we want to take a look at it. Okay, no problem. Let me see if I haven't missed anything. Okay. Question for the viewers: have any of you folks used reinforcement learning in production? Oh, nice. Matthew mentions that Matthew is using deep reinforcement learning for a personal project. And do you use a framework for it? Anything specific? Anything particular? I wanted to mention that Learner is built with just Python and scikit-learn. The agent is implemented as a class in Python. The neural network comes from scikit-learn multi-layer perceptron, and there is nothing too fancy. I think the complexity came from having it exposed as an API and being able to call those APIs in a scalable manner, so we can create hundreds of agents, thousands of agents, however many we want. I believe currently we run about 100 different agents in production. Yeah, so there is nothing too special about it. But I think if you keep the tools simple, it's actually a lot easier to navigate. And all the agents, so we have two different reward functions. Most of the agents use one version of a reward function. They all operate in different environments. So for example, we can have an agent for a particular TV model, for a particular version, with a particular set of tests, for example, audio. And that agent will be giving predictions for APIs and for that specific environment. And then we have kind of 100 of those agents for different set of hardwares and different set of inputs. Has anyone tried, I believe, SageMaker RL in AWS? I've seen presentation of it and it looked interesting, but I never tried to use it. Maria asked a question. So Learner is being used more as a form of aid to understand possible failures rather than replacing automating your development pipeline at Netflix. Yeah, that's correct. It's not in a state of replacing, it's in a state of kind of being in the shadows and doing the recommendations and optimizing the schedules, and then human at the end of the day have to go and look into the results of it. Okay, thank you so much, folks. Thank you for joining in and listening. I'll hope we get to connect again. Thanks a lot.